Hi, this is Physics, the chapter on transfer of thermal energy. Lesson 4, Radiation. In this video, we will deal with the physics concept of how thermal energy is moved from one place to another by radiation. So what are the learning outcomes addressed in this video? These are radiation heat transfer. What is actually radiation? Second, does radiation need any medium to transfer heat? And third, what affects the rate of radiation? So let's find out. Radiation is actually the transfer of thermal energy in the form of electromagnetic waves called infrared radiation. You will learn more about electromagnetic waves in secondary 3, so do not worry too much about this for the moment. Alright? So for thermal energy transfer by radiation method, we also know that it does not need any medium for it to transfer thermal energy, unlike conduction and convection heat transfer. Recall that in conduction heat transfer, this works very well in solids, and it also occurs in liquid, while convection heat transfer occurs only in liquids and gases, otherwise also known as fluids. So this is how the Earth is warmed by the Sun. The Sun, which is so much hotter than the Earth, transfer thermal energy by infrared waves radiation through vacuum to reach the Earth. In case some of you are unsure what a vacuum is, a vacuum simply means a place with nothing there. No gases, no particles at all. Of course, there could be some space rocks here and there, but most of the space between the Sun and Earth has nothing in it. You may want to do a Google search on your own to understand more about vacuum. Now, all objects or bodies emit or gives out infrared radiation. It's just that a hotter body emits more radiant heat compared to those which are cooler. The diagrams below shows the thermal image of some objects emitting radiant heat. Note the difference in color between the hand and the lizard in the diagram on the left. While on the right hand side, people shows up as tones of red and yellow, compared to the background walls, which shows up as purple or blue. So, the more radiant heat that an object gives out, thermal imaging shows this object in tones of red and yellow. So meaning that these objects over here will tend to give out a lot more radiation compared to those in blue or purple. So from the previous slide, we have learned that all bodies emit or give out thermal energy by radiation. In short, we can also say give out radiant heat. Now imagine that we have a case where there are only two objects. One very hot and the other one very cool. Both of these give out radiant heat as well. Since we know that the heat travels from hot to cold, the hot object effectively becomes an emitter of radiation, while the cooler object is effectively an absorber of radiation. This may sound confusing, but think about this. While the cool object is also emitting radiation, itself being the cooler object compared to the hotter one, also absorbs radiation from the hotter object. The amount of radiation absorbed by the cooler object is more than the amount of radiation it itself gives out. Hence, the effective situation here is that this cooler object will tend to absorb more radiation compared to giving out. So the final effect is that the cooler object becomes an absorber of radiation. So between the Sun and the Earth, we will consider the Sun to be effectively an emitter of radiation, while the Earth is effectively an absorber of radiation. Now let's try to understand further by what we have just shared in the last slide. Let's have a look at this case. You are going on a jog on a hot sunny day. Which t-shirt would you wear so that you will feel less warm? I'm sure your answer is black. So what is the difference in wearing the black and white t-shirt in direct sunlight? So recall from the previous slide about the case where it involves two objects, one hot and one cold. Well, for this particular situation, there is the Sun, which is definitely much hotter than the black t-shirt. We also know that both of them are also giving out or emitting radiation. But which? Is it the sun or the black t-shirt is effectively an emitter, and which is effectively an absorber of radiation? Well, for this particular case, the sun is effectively an emitter of radiation, okay? And while the black t-shirt will become an effective absorber of radiation from the sun. The case presented in this slide also reminds us that our daily experience is important to our understanding of physics concept. You can tell that black surfaces are better absorber of radiation compared to white. So this leads to the question, what other factors besides surface color affects radiation? Now, experiments have also proven that surface that is black in color and dull are better absorber of radiation compared to a surface that is silver and shiny. This experiment over here is one such case. A heat source, for example the light bulb, is placed at same distance away from the shiny aluminium and blackened foil. Both foils are wrapped around a temperature sensor. Once the heat source is switched on, the effect of temperature changes is monitored over some time. The result will be shown on the graph like this. Well, from the result itself, in the graph, this confirms that the blackened aluminium foil is a better absorber of radiation from the light bulb. Hence, this causes its temperature to rise faster compared to that of a shiny foil. So in summary, a dull and black surface are better absorbers of infrared radiation compared to that of a shiny foil. Now, interestingly, experiments have also shown that black and dull surfaces are also very good emitter of radiation. This simply means that black and dull surfaces are very good at giving out radiation. In this example, two identical sized cans contains hot water. The temperature of the hot water at the beginning of the experiment is the same. When the temperature of both cans are plotted on a graph, it shows that the black and dull tin shows a faster drop in temperature. This confirms that black and dull surfaces are better emitter of radiation as compared to a shiny silver tin. So in summary, a good absorber is also a good emitter of radiation. And dull black surfaces are very good absorbers and emitters compared to shiny surfaces. Shiny surfaces are also poor absorbers and emitters of radiation compared to dull black surfaces. We also know that shiny surfaces are also good reflector of radiation, while dull black surfaces are poor reflector. At this point, I would like to point out that reflecting heat is different from emitting heat, so do not mix up these two properties of a shiny surface. The table at the bottom over here summarizes what we have just talked about very nicely. So emitters are best when it is dull and black surface and being very poor when it is silvery and shiny. Reflectors, dull black are very bad or very poor reflectors compared to silvery surfaces. And lastly, absorbers, good absorbers are dull black surfaces compared to that which is a silvery surface. So besides color and surface texture, what other factors affects the rate of heat being emitted? One other factor is the surface temperature. A surface with a higher temperature will emit heat faster than one that is at a lower temperature. In the diagrams below, a barbecue pit is a lot hotter than a cup of hot coffee. Hence, the rate of emission from the barbecue pit is higher than that compared to a cup of hot coffee. The last factor that affects the rate of radiation is the surface area. For two objects of the same mass, material and external surface color and texture, the object with the larger surface area will emit or absorb infrared radiation at a higher rate compared to that with a smaller surface area. So, let's now apply what we have learned to a few real-life examples. For example, Why are solar panels painted black? Well, that is simply because black surfaces are good absorbers of radiation. Hence, this can absorb more radiation from the sun compared to a shiny or silver surface. Why do teapots and kettles have shiny metallic surfaces? The shiny metallic surfaces are poor emitters of heat. Hence, this will minimize heat loss from the hot drink which is inside the kettle. So this will help the contents inside these kettles to remain hot for a longer period of time. Now, one other use is the vacuum flask. This flask is very good at keeping its content hot, right? How it achieves this is by some special design that considered the way how thermal energy is transferred from one place to another. The first design feature is that it has a double wall glass container with a vacuum in between. This feature prevents conduction and convection heat transfer from the hotter content on the inside wall to those on the outside. Secondly, the silver walls on the vacuum side are poor emitter of radiation, hence preventing heat loss by radiation. Lastly, notice how the other parts of the vacuum flask are made from materials which are insulators of heat. The plastic cap, foam plastic support are all conductors of heat. Hence, this will prevent heat loss from the inside away to the surrounding by conduction. Now, I would like to challenge you to consider why a vacuum flask is also considered very good at keeping a cold content cold. Think about it. So, to summarize, radiation heat transfer. So, what is radiation? Right? It is actually a way of heat transfer by electromagnetic waves, in particular infrared waves. Does radiation need any medium to transfer heat? Well, radiation does not need any medium. It can happen through a solid, liquid, gas, or vacuum. Lastly, what affects the rate of radiation? There are three factors. First will be the color and texture of the surface. We know that now, black and dull surfaces are good emitters and absorbers of radiation. White, polished surfaces are the opposites. They are the poor emitters and absorbers of radiation. Also, do not confuse the emitters as reflectors. Both of these are not the same property. The second factor would be surface temperature, and the third factor would be surface area. So that brings us to the very last slide of this video lesson. I thank you for listening to this.